Offline reinforcement learning learns a policy from a fixed pile of old data. To stop the agent from over-trusting actions it never actually saw, it deliberately trains a pessimistic value function. A popular belief says over-pessimism hurts generalization, so researchers push the pessimism as low as possible. A 2026 paper from Delft turns that belief upside down. It is not how much pessimism you have. It is whether the pessimism respects the right symmetry. They prove it on a rotating reacher robot. The agent trains its arm at just 4 shoulder angles, 0-90, 180, and 270 degrees, but it has to reach the target at any rotation. Build 2 pessimistic value targets. The symmetric one stays invariant under rotation. The asymmetric one is subtly tilted. Distill a fresh network on each. The symmetric target holds test return at 0.99, even when you crank the pessimism 10 times beyond the maximum reward. The asymmetric target collapses, from 0.76 down to 0.23. Same data, same network, only the structure of pessimism differs. 2 theorems pin the mechanism. Theorem 1. If the pessimistic target respects the training subgroup's symmetry, the greedy policy is provably optimal on unseen test contexts with high probability for arbitrarily large pessimism. The sufficiency condition depends on the network, the data, the optimal value, and your confidence. It does not depend on the pessimism level at all. Theorem 2 plus a counter example. A milder but non-symmetric target can be arbitrarily worse than an overly pessimistic but symmetric one, even though both look optimal during training. At the extreme, pessimism cranked 10 times beyond the maximum reward. Start from the near zero baseline and both targets score identically, 0.76, by construction. Now push the pessimism to 10. The symmetric target's test return rises to 0.99. The asymmetric target's test return collapses to 0.23. Theorem 1 and Theorem 2 rendered in 2 diverging bars. More pessimism applied symmetrically costs nothing. Less pessimism applied the wrong way is fatal. Sweep the pessimism level from near 0 up to 10. The symmetric test return line climbs and saturates at 0.99. The asymmetric line only ever falls 0.76, then 0.73, 0.68, 0.23. The asymmetric curve never once beats the symmetric one. The collapse is monotone. Generalization is governed by structure, not by amount. Picture a pattern invariant under rotation. Spin it to any angle and it looks identical. The arm reaches true at every orientation. Now picture a pattern that only looks right at the 4 training angles. Rotate it 45 degrees and a suboptimal action outweighs the optimal one. The greedy policy locks onto the wrong move forever and the episode returns 0. Symmetry is the whole game. In real offline RL, you cannot choose a symmetric target by hand. The data dictates its shape. So enforce symmetry with data augmentation. The winner is a consistency loss on the network output during policy extraction. On a mixed quality dataset, no augmentation scores 0.34, standard augmented training reaches 0.68, and the output consistency loss hits 0.96, a 0.62 gain. The same pattern holds for CQL, and it carries the hardest, suboptimal dataset too. 3 honest caveats. First, at near zero pessimism, the symmetric and asymmetric targets are identical by construction, so the contrast is designed there, not independently measured. Second, the asymmetric target's training return also collapses at extreme pessimism, so part of the test collapse is a training artifact, though the monotone trend still holds. Third, the output consistency loss is the strict winner only on mixed and suboptimal data. On expert data, it ties within error bars, and the whole study is 1 environment and 2 algorithms. The contribution is the mechanism and the reframe, not a new state of the art. Generalization in offline RL is a symmetry problem, not a pessimism problem. Respect the symmetry, and pessimism is free. Break it, and no amount of caution saves you. A consistency loss during policy extraction is the practical lever. Subscribe for the next breakdown.